I'm going to quickly do the variance covariance matrix. We generated the beta last time, so I want to quickly do the variance covariance matrix before we go to the R. So this is what we want to do. Prove that the variance covariance matrix, so that's the variance of the beta, is equal to the expected value of this. And finally, it is the sigma square over the x prime x to the power negative 1. Now this sigma square is the variance, and the square root of this variance is the standard deviation. Okay, so keep that in mind. Keep that in mind. So I'm going to get a new page, and then we're going to derive this together. And this is something that you have to learn it. You have to know how to do it at a level like this. Okay, you have to know how to do it. Okay, so let me rewrite it all here. Okay, what you saw, we're going to rewrite it all here. That we are going to prove that the variance of beta cap, we are proving that it is equal to the expected value of beta. Is equal to the expected value of beta cap minus beta. Beta cap minus beta prime, and then beta cap minus beta no prime. Okay, and this is equal to sigma x prime x to the power negative 1. Now this last part, which is the sigma x prime x to the power negative 1, that is what is known as the variance covariance matrix. That is known as the variance covariance matrix. So we are going to use our understanding of two things. One, understanding of the assumptions of regression, and then our understanding of what we derived last time, which is the beta cap, the OLS value of the beta parameter is equal to the we indicated that. Let me just remind you, I mean, this one, when I write it down, is the best way to capture it. This is what we wrote the last time. We indicated that beta cap, which is the OLS, was equal to x prime x to the power negative 1 x prime y. Okay, you remember this? This is what we proved the last time. That's what we proved. So we are going to do some substitution and analysis, and then we'll be able to get it. Now, first thing, we are going to substitute the value of y here. What is y? Well, you might remember that y is equal to x beta, and then we have the epsilon. X beta plus epsilon. This is y, which is in a matrix, because we said that the x's are plenty, so we don't want to make it plenty. We want to make it smaller, and we know where this is coming from. So wherever we see y in the second situation here, we're going to put it there and then derive something very beautiful. Okay, we're going to do that first. So this can be equal to x prime x to the power x prime x to the power negative 1, then x prime y, and instead of the y, I'm putting in this, whatever is here, I'm putting it there, so that becomes bracket x beta plus epsilon. Ladies and gentlemen, I'm not changing anything. It's just a simple way. Okay, that's what we do. So we can now expand it. Okay, because you can see that this x prime is multiplying this thing. So I can expand it. So let me expand it quickly. So that gives us x prime x to the power negative 1, and then x prime, it will be multiplying the x beta. So you have x beta, then plus the x prime will also be multiplying the epsilon. So you have x prime multiplying epsilon. So that is what you have there. Okay, I can now, see some beautiful resemblance here. If you can't see it, I can see it. One of the first thing is this. We are going to take the expected value of this beta. The expected value of this beta. We're going to take it. So what are we expecting this coefficient to be? This beta, cap. What are we expecting it to be? Now watch it. If you look at this first part here, and then you look at this second part here, do you realize that this second part is to the power -1? Okay, it has a transpose, it's to the power -1, but we don't write it, but it's there. It's to the power -1. And this is the same thing here. It is also to the power, sorry, this first part is to the power +1. We don't write a 1. And this is to the power -1. So you have -1 plus 1. And so the whole of this would be something like this. X prime x to the power -1 plus 1, which is 0. And of course, any number raised to the power 0 is 1. Okay, so I'll attach my beta here. Then, if you should multiply, if you take the expected value of this, if you take the expected value of x prime epsilon, okay, that's 0. That's 0. Why is it 0? Because there's an assumption called zero mean assumption in regression. And zero mean, the word mean is expectation. So zero mean means the expected value. So we already know from the assumption of, zero mean, we said the error term is always, and this is the error term. The epsilon is the error term. The error term is normally distributed. It is IID, normally distributed with a zero mean and a constant variance. Zero mean and a constant variance. Of course, this is a constant variance here. So that zero mean will mean that even if you take the expected value, please note the expected value of something means the mean of that thing. And here, the mean of this epsilon is 0. So the whole of this is 0. Okay. And so we can say conclusively that the expected value of beta cap is going to be this beta. Because this part here will be 0, will be 1. Because any number raised to the power 0 is 1. So you get 1 times beta, which is beta. Now, ladies and gentlemen, this means this is what is known as unbiased. Okay, so the expected value of beta is equal to the true beta. So this is why we say that the OLS regression parameters or estimates are unbiased. Okay, unbiased. Okay, unbiased. Of course, there's a big term, other things that you have to check to eventually arrive at other things, which we sometimes call the blue. Okay, best linear unbiased estimator. But the unbiasedness is what we just demonstrated here. Okay, unbiased. Unbiased means that the expectation of the error, the expected value of that beta cap is the true value that you will find. Okay, we indicated the last time that the true value is not known, so we've got to estimate it. That's why we put a cap on it. It's not known, so we've got to estimate it, and that is what gives us this. So keep this in mind. So whatever we know, the expected value of beta cap, we know that is going to be what? Beta. Keep that in mind. The expected value of beta cap is going to be beta. So don't forget that. Keep that in mind. So with that assumption, we can now proceed with our variance, okay, of beta cap. So we've been able to prove that the mean is 0. Okay. So what is the variance of beta cap? What is the variance? And in fact, this is what we are trying to prove here, okay, at the top. This is what we are trying to prove. The variance of beta cap is what? How do we get that? Okay, and we are going to use the values that we got, the assumptions of the values we got. Okay, we are going to put it there. Now, the first thing you want to understand is this. The first thing you want to understand is that this was giving us what you see in there, the beta cap here. Okay, so the expected value of beta cap minus beta prime, and then beta cap minus beta no prime. Now that beta cap that we know here, we know the value. If we take this expected value of beta cap, we know what it is. So we can replace wherever we see beta cap, we can replace it with something. Wherever we see beta cap, we will know what to replace it with. So what is beta cap here? Well, let's go back. Okay, watch it here. That's it at the top here. That's beta cap. So wherever we see beta cap, we're going to substitute x prime as all of that information that you see here. In fact, let me just note it with this for you. So we are going to see this. Okay, we're going to replace it with that. So when we go to the next page and we are writing this, we're going to replace it with that. It's going to be a bit long, but you have to follow me to be able to appreciate what is happening now. So this is equal to the expected value, okay, of beta cap minus beta prime, and then beta cap, okay, minus beta no prime. Okay. No prime. Now, and then we know what this beta cap is. So this is going to be equal to, oops, and I'm deriving this thing for a reason. It's called a variance covariance matrix. Okay. This is equal to the expected value of beta cap, and beta cap itself is x prime x to the power negative 1, okay, and then x prime y, okay, and then now that's the beta cap, and then minus, so I can put all of this in a bracket, and then you have minus beta, okay, I can put all to the prime, let me delete this and then indicate the prime there, and then you have the same thing on this side, the same thing. So I'm going to write, okay, x prime x to the power negative, and remember these are just matrices, okay, x prime y, okay, minus beta. We are going to take the expected value of all that. But watch something, because it's very beautiful and interesting. We know this value. We know the y. Okay? We know the y. If you can remember, y was, and again, I need to take you back because some of you get a little bit confused. Watch y. Y is x beta plus epsilon. S beta plus epsilon. Do you remember that here? That is y. X beta plus epsilon. So I can put, wherever I see y, I can put what? X beta plus epsilon there. So let's go and put that there. Now, so if wherever I see y, I'll put x beta plus epsilon. So I can rewrite this whole thing as expected value x prime x, okay, to the power negative 1, x prime. Instead of y, I'll put x beta plus epsilon. Then I have my minus beta already. Okay. I'll close this all to the power prime. And then I do the same thing here. X prime x, okay, negative 1, x prime. Instead of y, I'll put x beta plus epsilon, and then minus that. Now, ladies and gentlemen, once you have it like this and you understand where they are coming from, there's a lot of cancellations that you can do. First thing, you will notice that this x beta plus epsilon, this part here, okay, x beta plus epsilon, you can expand it. We have already done the expansion of it. And when we did expansion of it, this is what we had. We eventually had what? Okay, we had expected value of beta cap to be this. Of course, we got it to be x prime x to the power negative 1 raised to the power 0 and all of that. We got that. So we can do, that's the same thing that you are seeing here. Okay. To the power negative 1 and 0 and all of that. But don't forget that it's a prime as well here. Now, this whole thing, when we take its expected value, okay, and I'm going to do inequality sign. When you take its expected value, you are going to get beta. Because as for the expected value of the error term is nothing. The expected value of the error term, we know that to be what? 0. So eventually, we are going to have this to be what? To be 0. But remember this. There's a plus in between. Okay, let me use a different color too for you to appreciate this. There is a plus. Okay, there is a plus here. There is a plus. So if you should expand it, you'll be left with epsilon here, multiplying this part. Okay. If I should expand this thing, it's going to be quite complex. So, but just understand that this whole thing there is expanding it. So if this whole thing is multiplying the x beta, then we are left with the expected value of beta. Okay. And then this second part here will have this whole upper part. The second part, the epsilon, will have this whole upper part. Okay. And so if it is going to have that whole upper part, then we are going to be left with x prime x to the power negative 1 x prime epsilon. Okay. That's what we are going to be left with. X prime x to the power negative 1 x prime x epsilon. Okay. So we are going to have plus x prime x to the power negative 1 x prime epsilon. And then finally we have our minus beta. And then we have this. Now, that's the same thing on the right hand side. That's the same thing on the right hand side. So it means that we're going to have the right hand side beta plus x prime x to the power negative 1 x prime epsilon minus beta. Okay. Now watch it. You see that the beta and the beta will cancel. The beta and the beta will cancel out. So that is gone. Whether they have primes or they don't have primes, okay, they are gone. So this means that we are left with expected value. Okay, now it's getting smaller. X prime x. Okay, I can use it. Curly bracket. X prime x. Okay, to the power negative 1 x prime epsilon. Okay, that's the first one, which is now, of course, it has a prime. It has a prime, so let me put a prime there. Then there's the same thing, which is x prime x to the power negative 1 x prime epsilon. That one does not have any prime. Okay, let me see whether somebody has a question. So somebody said I should go over the previous one. Don't worry, I'll go over everything, okay, at the right time. So once you have this, at this stage we are good to go. Now remember, some of them have primes here. Some of them have got primes, others do not have prime. There are a few things you need to learn here. Okay, you need to learn in matrix. Just quick one. Let me go to the next page. Quick one. Few things. The first one is this. The first one is X transpose. X transpose. When you have anytime, and this is anytime you have X transpose times X transpose. X transpose times transpose. And I think that the last time I told you to just learn a little bit of that. X transpose times transpose. What will be the value? This one you either know or you don't know. X transpose times transpose. That is like X prime prime. That's what it means. X transpose times transpose. What would the value be? If you have a little bit of matrix, you know that that is X. It's like saying X prime or prime. That is what? X prime or prime is X. That's what I'll be doing. X prime or prime. That is X. And that is exactly what we are doing. Okay. Don't worry, just focus. Just focus. Just focus. And so we are now ready to be able to apply that principle. Okay, so we're going to apply that principle in our own here. So watch me here. Each one of this, watch it. This one has a prime, so it will be epsilon prime, and this one will be X transpose times transpose. So that will be X. So watch this. This one will be epsilon prime, which is nothing. Okay, because we are going to take the expected value. X prime prime is X. And then when you bring this prime to the ones here, it will turn and everything will be like the same thing. It will turn and everything will be like this. I want you to understand this first part, okay? That if you bring this prime, if you bring this prime and attach it to this, you get X, okay? And if you give that prime to each one of this, the whole thing will swap the other way, okay? It will swap the other way. And that's the principle that we're doing. So eventually, we are going to have this. Have the expected value, the variance is equal to the expected value of X prime X to the power negative 1, okay, because I told you that nothing will change in the first part. And then you are going to have, and I'm going to go back here, just watch. You are going to have X for this. Now this one has what? No prime. Look at it at the top. These ones, all of them had prime, but this one had no prime. So we have X eventually for this, and this one has prime. So I can put the two there together. Okay, maybe you wouldn't see, but I can put the two there together. So that will give me, I'm going to add that here. That will give me x prime x. All right. Now let's go back to the formula. You see that again, epsilon and epsilon are there, which are multiplying. Okay. And one of the epsilon has a prime. Look at it. The first one, which is the epsilon here, has a prime. So I can add that to the next part. And then I can have epsilon prime epsilon, because the other one doesn't have a prime. And then finally, let's go back. Finally, you see that we have x prime x to the power negative 1. Okay. X prime x to the power negative 1. So I will add that there. And so you get x prime x to the power negative 1. Finished. Now, when you look at this, watch it carefully. There's no problem. Watch it here. You can see that this and this will cancel. Do you realize that? Because 1 is to the power negative 1. 1 is to the power invisible positive 1. So expected value of... So whilst this one goes, we will now be left with something that looks like this. We are now going to take the expected value of the middle one here. I'm going to take the expected value of this. Okay. So I'm going to take the expected value of epsilon prime epsilon. Now, we can't take the expected value of these metrics. Okay, we can't take the expected values, and so we just write them just as it is there, and so that will give us what? X prime x to the power negative 1. So our next thing is, what is this? Okay, if you take the expected value of the error term square, more or less, this is the expected value of the error term. This is called homoscedasticity assumption. This is known as homoscedasticity. So it's just like taking expected value of epsilon square, and that alone is homoscedasticity. And homoscedasticity is given by, forget about this one, because this one is a matrix that cannot be altered. This alone is equal to the variance. Okay, the homoscedastic assumption. And therefore, we can conclude that the variance of the beta cap, okay, is equal to sigma square x prime x to the power negative 1. And this is what is known as the variance covariance matrix. I can put quote erat demonstratum to indicate that we have finished our derivation. Now, somebody might be sitting down and be saying, what is all this? And this is it. This is what is known as the variance covariance matrix. What is that? And I'm going to give you some importance of the variance covariance matrix right here. Okay. In general, the variance covariance matrix is such that you have the variances on the off diagonals, as you see here, and then you have the covariances on the off diagonals left and right. The variance and the covariance. I'm telling you, this is a very powerful thing in regression. Why? Anytime you are doing any regression, our goal is to find the parameters and to determine whether those parameters are significant. The diagonal elements of the matrix, which I just showed you here, those diagonal elements of that matrix that you know. Let me use this pointer to tell you something. Those diagonal elements, okay, that you see here, they are very, very important, very usefully important. First of all, note that the beta cap is normally distributed, and it is the expected value is supposed to be beta. We proved this, and now we've been able to prove that the variance is equal to that. Okay. So you have the variances of the diagonals, okay, and then you have the covariances on the off diagonals. Now, what are variances? Variances will measure the variability or the spread of the data. It's important. You need to know how spread the data is. So knowing how to derive the variances is crucial. Covariances will tell you the extent to which corresponding elements from the two sets are ordered in such a way that they can move in the same direction. So all of these help us to get a clearer understanding of the statistic, how a particular statistic vary and then how they co-vary. Now, let me tell you a practical use of this. It is often used to calculate standard errors. Now, when we get to the regression very soon, you'll see that the coefficient, the estimate, divided by the standard errors will give you the t statistic or the t value. And then you read the t value from the table and you get a p-value. It is a p-value we normally use to determine whether a particular coefficient is significant or is insignificant. So the last point here is a very important, but we can determine the measures of goodness of it. We can do that. We can find interpret coefficients, linear model, test of partial and joint significance. This thing that we derived right now can help us to be able to arrive at that section. So it's important to know at a higher level the derivation of the variance covariance matrix.